All right, hi everyone. Welcome to Math Competitions 2, which we're going to be starting momentarily. And as of now, I'm going to quickly so the reason I don't have my video on is because for some reason Zoom seems to break whenever I turn on my video. So hopefully this will get fixed by next week, but we'll see. And I'm also going to quickly change the chat to all panelists because otherwise I think my computer might also break. So yeah, we'll see about that. But anyways, so since some people are still coming in, I'm going to quickly reintroduce how to submit homework, where to find resources, where to ask questions, and that sort of thing, in case you weren't here yesterday. So I'll quickly share my screen for that. Yeah. So if you can see my website right now, this is just the Kid Teach Kid homepage. So in order to go to resources, just go to classes and then summer camp class resources, and you should be able to access everything, or as soon as we put it up at least. And then for question submission, go to classes, question submission. If you would like to take help with the student survey, you can go to student survey. And then with homework submission, you can go to classes and then homework submission, which, yeah, where you pretty much just upload homework. So yeah. All right. And we're going to be starting in like 1 minute because I think some people are still getting in. So yeah. All right. Someone asked, is anyone talking? Yes, I am talking. Can we have polls? I'll try my best. Let's see. Can you still predict the future? Somewhat, I guess. So yeah. Hi. Hi everyone. Welcome. All right. So since most people seem to have gotten into the meeting by now, I'm just going to share my screen and then we'll get started. Oh, and by the way, if my computer randomly crashes at any point, hopefully I'll try my best to like get back into the Zoom as soon as possible to make sure that the meeting still runs. So if the meeting just suddenly crashes, just try to join back and hopefully I'll have it fixed soon. So yeah. Okay. So for today, we're going to be quickly talking about auxiliary constructions in geometry. So what we're going to be doing is we're first going to talk about the definition of auxiliary constructions, then go through the introductory problems, go through some harder problems, and then finally, if we have time, we'll get to some challenge problems. Yeah. I thought that this course doesn't have homework. You don't have to do, well, it's not required, but it's just recommended because it helps supplement the material that you learn in class and make sure that you can understand better. So yeah. All right. So without further ado, let's get into the definition of auxiliary constructions. So the first question is, what are auxiliary constructions? So even though the word might sound kind of long and big, it's not really, because they're basically just something you can create to make the problem easier. So for example, an example of an auxiliary construction might be to draw in a helpful circle. So for example, if we have a cyclic quadrilateral, which I believe Andy taught a bit ago, then if you draw in the circle, sometimes it'll help. Or other times when an auxiliary construction will be helpful is when you have two parallel lines and you can construct a line parallel to the other one to create more similar triangles. Another type of auxiliary construction is called a reflection. And my favorite example is the orthocenter reflections, even though this is a bit advanced. So the orthocenter is the intersection of the three altitudes of a triangle. So if you can see in this triangle right here, the orthocenter would be here, so H, or that's what we generally call the orthocenter, at least, H. And then one interesting property about the orthocenter is that you can reflect. If you reflect the foot of the altitude of the orthocenter, then it lies on the circumcircle. So this is the circle. This is the circumcircle of the triangle. Okay, I'm sorry, I can't draw very well, but you know. So then if you reflect the orthocenter onto here, it'll be a point on the circumcircle. So that's always pretty cool. So that means that these two are equal, these two are equal. And then if you reflect it here off this point, then these two will also be equal. So that's another type of auxiliary construction that we'll hopefully be trying to cover today. Or hopefully we have enough time. Great drawings. Yes, I know. I have very great drawings. All right. So, one more I forgot to cover is about tangencies. So tangency with circles or lines is a common way to for problem writers to create problems. So for example, if they create two tangent circles, or if they have a circle tangent to a line, then this is something that people really love to create problems with. then most of the time what you want to be doing is like connecting the two centers, because we know that it goes through the tangency point right here. Or if there's a line tangent to a circle here, then most of the time we're going to draw the line connecting the circle to the tangency point because it hits at a right angle. So yeah, that's pretty much what auxiliary constructions are. Are there any questions so far? Let's see. Can we use Q&A for chat? Probably not, because other people can't really see it. So yeah. What are, is that a muffin? No. All right. So yeah, now we're going to be getting on to tangency in a circle, which is our first introductory problem. So if we have that ABCD is a convex quadrilateral such that angle ABC equals angle ACD, then, and let point E be a line on AD such that angle ABC plus angle BEA is equal to 180, then given that AE is equal to 6, CD is equal to 4, find the length of AD. So AD is right here. And I'll give you guys like 2 seconds, or okay, not 2 seconds. I'll give you guys 30 seconds or so to think about the problem and what we might want to try doing here. All right, so hopefully now that you've had enough time to think about the problem, we're going to quickly get into the auxiliary construction that we're going to be using. So one thing we know is that in a quadrilateral, oh shoot, whoops. One thing we know is that in a quadrilateral, if two opposite angles sum up to 180, so if these two sum to 180, then we know that the quadrilateral is cyclic, or that means that it can be drawn, or a circle can be drawn around the quadrilateral. And yes, I know I'm great at drawing circles, so you know. And the thing is, we can see here that angle ABC plus angle BEA is equal to 180 degrees. So, wait, shoot, hang on. Wait. Okay, whoops. I think I wrote the problem wrong. Sorry, this was supposed to be a C. That was an accident. So we know that angle ABC plus angle AEC is equal to 180. So as a result, since these two angles sum up to 180, that means that we can draw a circle around the quadrilateral. So that's going to be pretty helpful. Okay, I'm sorry, guys. Like my circles are just like potatoes. All right, great circles, great circles. Now, anyways, now that we know that quadrilateral ABCE is cyclic, we look at the rest of the things that we are given. So we know that side AE is 6, as you can see right here, and then side CD is equal to 4. However, we also realize at the beginning that it says that angle ABC equals angle ACD. So angle ABC is equal to angle ACD. And I'll quickly mark that in red so that it's easier to see. And then one common property of circles is that, for example, if we draw the circumcircle of a triangle, and then we draw the tangent line at this point, then we know that these two angles will be equal right here. And if we look at this diagram, if we focus on triangle ABC, oh shoot, whoops. If we focus on triangle ABC and we look at angle ABC and angle ACD, then since we know that the red angles are equal, this means that line CD must be tangent to the circumcircle. So that means that we know that this line right here must be tangent. So does that all make sense so far? Let me quickly look at the questions. The chord is perpendicular, right? Yeah, line CD is tangent to the circle. Okay. So now from here, since we know that line CD is tangent to the circle, then we can consider the power of point D to the rest of the circle. So we know that so if we look at the power of point D, we can calculate it in two ways. We can calculate it as CD squared, And we can also calculate it as DE times DA. And this is because CD is tangent to the circle. So as a result, if we look at what we have, we know that CD is equal to 4. So we can say that 4 squared is equal to DE times DE plus 6. And then finally, if we solve for DE, which we can do with like quadratic formula or something, then we can get that DE is equal to 2. From here, since we know DE is equal to 2 and EA is equal to 6, we can get that 2 plus 6 is equal to 8, which is our final answer. So yeah, let's see. Let me quickly look at some of the questions. So what does tangent mean? Oh, so tangent, so if a line and a circle are tangent, for example here, that means that the circle and the line intersect at only one point. Oh, whoops. So like here. Whereas most of the time, if a circle and a line are not tangent, that means that they either intersect at 2 points or they don't intersect at all. Why is it called Sage's math notebook? No reason. And yeah, okay. Does anyone have any more questions? Can you explain the tangency triangle thing? Oh, okay, sure. So this is sort of like a common power of a point configuration, but whenever you have I'll try to do this in a different color. But whenever you have a circle, and then you have a triangle like this, where all 3 points of the triangle are on the circle, if you draw a line tangent to the circle at one of the points, like right here, then we know that this angle must be equal to this angle. And as we can see in this diagram, we are given that the 2 red angles are equal. And as a result, we know that CD must be tangent to the circle. Is this problem from a competition? Oh no, I created this problem, which is why it's kind of weird. What grade is this class for? This class is mainly for AMC 10, sort of mid to late AMC 10 competitions, and probably early AME. So, but for grade level, it doesn't really matter. It just mainly depends on if you think you can gain things or learn stuff from the class. So yeah. All right. So now I'm going to be quickly moving on to the next problem, which is more tangency on a circle. And this problem is from the AMC 10. So 2 circles of radius 5 are externally tangent to each other and internally tangent to a circle of radius 13 at points A and B, as shown in the diagram. What is the length of AB? And I'll give you guys some time to think about the problem and think about how we might do this. All right, so hopefully you guys have had enough time to think about the problem. So as we can see, we want to find the length of AB, which is this segment right here. Oh, whoops. But the thing is, we also know that each of the 3 circles is tangent to the other. So if we draw the centers of each of the circles, like right here, that since the circles are tangent, we know that we can draw a line connecting their centers. So like this. That also includes the tangency points A and B. And we can also draw one like this and one like this. Oops. Oh, shoot. So from here, we also know that each of the smaller circles has a radius of 5. So we can label that here. So this is radius 5, radius 5, radius 5. And we also know that the larger circle has radius 13. So we know that that means that this length is 13. Now, if we look at the problem, then we realize we can draw a line right here that sort of bisects the sides and is tangent to both circles. So we can draw this length right here. And as a result, since it bisects, we have that this is 90 degrees. And since we know that each of the smaller circles is radius 5, that means that we get that this has side length 5, and then this has side length 8. So from here, since we know, if we look at the smaller triangle right here, we can see that it is similar to the bigger triangle, which is this one, as both of them share an angle, and they both have a 90-degree angle. So as a result, if we use similar triangles, we can get that 8 to 5 is equal to 13 to x, where x is this segment right here, to get that 8x is equal to 65. So we can solve that x is equal to 65 over 8. And then from here, since we want to find AB, which is 2 times the length of x, we can get that 2x is equal to 2 times 65 over 8, which is equal to 65 over 4. So yeah, that's our final answer. And before we move on, I'll answer a few questions. So how is it 5? So the diagram, if we focus in on the two smaller circles, which are right here, then we know that each of them has radius 5 because it's given in the problem. So when we draw this line connecting them right here, the reason it's 5 is because this is the tangency point. So we know that since each of the circles is radius 5, each of these two miniature lengths must both be 5. Okay. Yeah. Any other questions? Which problem is this on the AMC 10? I can't actually remember. I think it was somewhere around 15 or 16. Yeah. All right. So it doesn't look like there's any other questions. So I'll quickly be moving on to the next type of auxiliary construction, which is similarity constructions. And I highly recommend that you guys pay attention to this one, because I remember I used to miss these types of questions all the time because I never knew where I was supposed to draw the extra lines to create similarity. But after a while of doing enough of these types of problems, I eventually got the hang of it. And I may have missed like this problem 10 times. Okay, probably not 10, but somewhere closer to 6 before I finally understood what I was supposed to do. So I'll give you guys some time to read the problem and think about how to do it. All right, so now that hopefully everyone has had enough time to read the problem, I'm going to quickly start. So one thing that whenever you have a configuration like this, where we have a rectangle and we draw one of the diagonals and we know some of the side lengths, the first thing that I have come to always think of doing is extending this side extending side AE until it meets somewhere with BC. So we can call this point like G or something. Whoops. And the reasoning behind this is because by doing this, we create two different pairs of similar triangles. We can see that triangle ADE is similar to triangle GCE. And we can also get that triangle AFD is similar to triangle GFB. So as a result, just by drawing in this extra line, just by drawing in these extra two lines, we can see that we now gain two similarities, which are really helpful because they allow us to sort of length chase our way through the problem. So yeah. From here, the first thing we're going to use is to use the similarity ADE is similar to triangle GCE. So if we use our length ratios, we can see that DE to AD is equal to EC to CG. And then we can plug in our lengths to get that 6 to 8 is equal to 18 to CG, from which we get that CG is equal to 24. So now we have CG is equal to 24. All right. Now that we have that, since we know that this is a right angle, we can use Pythagorean theorem to get the length of EC which is 30. Because 18 squared plus 24 squared is equal to 900, and the square root of 900 is 30. So now that we have that, we're going to try to be using the similarity FBG, or AFD is similar to triangle GFB. Now noting, since we know that this is a rectangle, we know that side AB is equal to 24 because AB is equal to DC, and then side DC is just equal to DE plus side EC, which we already know the lengths of. So, and since we also know that since ABCD is a rectangle, side AD is equal to side BC. So this is equal to 8. So as a result, we know that the similarity ratio between triangle AFD and GFB is equal to AD to BG, which is actually equal to 8/32, which is equal to 1:4. However, by using similarity ratios again, we also know that this is equal to AF to FG. And if we set AF as X and we set length EY here as Y, then this implies that 1/4 is equal to X to 30 plus Y. All right, so now from here, the one last step we have to do is identify the last pair of similar triangles to finish the problem. So, and we can see this because since we know that lines AB and DE are parallel, we know that this angle is equal to this angle. And we also know that this angle is equal to this angle. So as a result, we have that triangle AFB is similar to triangle EFD. And from here, we can use our length ratios to get that AF to FE is equal to AB to DE. And if we plug in our variables and numbers, this should give us that X to Y is equal to 24 to 6, which is equal to 4. So from here, we get that 4Y is equal to X. Now, if we combine this with the previous ratio that we did, which is 1/4 is equal to X over 30 plus Y, we can get that 30 plus Y is equal to 4X. So if we plug in for X, we can get that, if we substitute in X is equal to 4Y, we can get that 30 plus Y is equal to 16Y. And from here, it's easy to see that Y is equal to 2. And now, since 4Y is equal to X, we can just get that X is equal to 4 times 2, so X is equal to 8. And that is our final answer. So any questions? You could use coordinate geometry. Oh yeah, that's true. But I'd say that learning similar triangles is sometimes a bit more helpful because it sort of builds fundamentals for later problems where similarity is much more important than coordinate bashing, because coordinate bashing can kind of get ugly. Yeah. Oh shoot, that is true. Oh yeah, that is true actually. I think some of you guys pointed out that you could only use the similarity between ABF and DEF. And I think that's actually true because you know that AE is equal to 10. So you can use that similarity ratio instead of just drawing all these extra lines. But either way works, even though the way you guys mentioned was actually a lot easier. So yeah. So for all of you people, for everyone who's saying that you only need to use ABF to DEF, that's true as well. Okay, so I'm going to be moving on to the next problem now, which is about the power of altitudes. And this is from an Amy problem. And even though this was a number 1, I think that this was actually unexpectedly tricky for a lot of people. And a lot of people ended up missing it, even though it was a number 1. So, and also it's from the Amy, so you can't really expect it to be too easy. And I'll give you guys some time to read the problem. All right, so hopefully you guys have had enough time to read the problem. So I'm going to quickly start by mentioning that a lot of people did solve this problem by using coordinate geometry, because if you set points for A, B, C, and D, you can get their intersection, which allows you to solve the problem fairly, I'd say safely, even though it does take kind of long. But the thing is, if you can identify the correct auxiliary constructions to make here, then the problem actually becomes a lot simpler. So the first thing we should notice is that we're trying to find the area of this region right here. So let's start by calling the intersection of the points, let's call them like F or something. Sorry, whoops. Let's call this E, because we've used A, B, C, and D already. But the thing is, we already know the base of triangle AEB, and now since we want to find the area, all we want to do is find the height. So if we draw the height here, then let's call this point like F or something. But the thing is, since we can see that we want to find the area of triangle EFB, because it's half of the area of triangle EAB, then if we extend from point D in altitude to line AB, then this actually almost immediately solves the problem. Because so let's call this point like G or something, because we can see that triangle EFB is similar to triangle DGA. So now all we have to do is find the height of triangle DG and find the length of GA, and we'll be done with the problem. And we can do this by setting some variables and using the Pythagorean theorem twice. So if we use Pythagorean theorem on AGD, we will get that x squared plus y squared is equal to 100. And if we use the Pythagorean theorem on triangle BGD, we will get that x squared plus 9 plus y squared is equal to 289. And from here, if we subtract the equations, we can get that x is equal to 8 and y is equal to 6. And if you look at it, this actually means that AGD is a 6, 8, 10 triangle, and then DGB is a 8, 15, 17 triangle. So both of which are interesting Pythagorean triples. Oh wait, whoops, this was supposed to be DGB. So now from here, since we know the lengths of DG and GA, we can just finish the problem, because by using the similarity ratio, we can get that EF to FB is equal to DG to GB. And from here, plugging in everything we know gets us that 8 to 15. Wait, sorry. Oh, sorry. It gets us that EF to 9 over 2 is equal to 8 to 15. And solving for EF gets us EF is equal to 12 over 5. And now, since we want to find the area of the triangle, all we have to do is multiply EF by AB to get 9 times 12 over 5 over 2 is equal to 54 over 5, which is the final area of the triangle. And the answer asks for m plus n, but I'm too lazy to do that, so you guys can do that yourself. All right, so I think that this is actually one of the better examples of auxiliary constructions, because if you don't use auxiliary constructions here, then you might have to resort to coordinate geometry, and most of the time that does end up taking a while. So yeah. Does anyone have any questions? Okay. So now we're going to be moving on to the last introductory problem, which is about completing the figure. And I think this is actually a fairly textbook example of how auxiliary construction should work, and also about how much variety you can use when sort of creating auxiliary constructions, because I think this is a sort of more famous way of using them. So yeah. And I'll give you guys like another 30 seconds to read the problem. Oh shoot, whoops. I just realized I actually typoed this question. This is supposed to be equal angular, my bad. All right. All right, so hopefully you guys have had enough time to think about the problem. So we're gonna quickly continue. So if we start by drawing the hexagon, A, B, C, D, E, then it should look something like this. And excuse my poor drawing skills, but yeah. Where this is A, B, C, D, E, F. And if we label all the sides, we know that AB is equal to 8, BC is equal to 9, CD is equal to 10, and DE is equal to 2. And actually, if you've seen this problem, then you probably know that the auxiliary construction we're going to use is to just turn this equal angular hexagon into an equilateral triangle. Because since we know it's equal angular, this means that all of the angles are 120. So if we draw in these sides right here, then that means that this will be 60 degrees, and this will be 60 degrees, and this will be 60 degrees, which means we have an equilateral triangle. And we can do that for all of the sides to get that this is 10, this is 10. We can do it for this side as well. And since all of these angles are 60 degrees, we have that the larger triangle we just created is an equilateral triangle. So right here, this big triangle. So as a result, we know that all of its sides are equal. So we can get that this side is 8, and then this side is 10. And then from here, since we know that the long side is equal to 8 plus 9 plus 10, which is equal to 27, then we have that both of the other sides must be summed to 27 as well. So if we call EF as X and AF as Y, then labeling all the other sides, we can get that X plus Y plus 8 is equal to 27, and X plus 2 plus 10 is equal to 27. So from here, we can just solve the system of equations to get that X is equal to 15 and Y is equal to 4. And then since we want to find EF minus AF, we can just do 15 minus 4 is equal to 11. So yeah. Any questions? So what equal angular means? So equilateral, which is what I originally wrote by accident, just means that the triangle has all of its side lengths equal and all of its angles are equal. So for example, a square would be an equilateral figure. A regular pentagon would be an equilateral figure. So what equal angular means just means that all of its sides, just means that all of its angles are equal. So in this hexagon, it just means that all of the angles are 120 degrees. Why do you need to do X plus 2 plus 10? Oh, so that way we can solve for X. Because if we just use X plus Y plus 8 is equal to 27, then that's not enough to solve for both variables. And yeah, equilateral means that all the sides are the same. We know that 8 plus 9 plus 10 is equal to X plus Y plus 8 because we know that the length of this side right here is equal to 27. And we know that the length of this side is equal to X plus Y plus 8. But since we know that all of the angles of the triangle are 60 degrees, we have that all of the sides of the triangle are equal, which is how we got that. So now that we're finished with the introductory problems, we're going to be moving on to the sort of harder problems, or not as much introductory. So this is the first one, which is from the AMC 10. And if we let sides A, B, and AC of equilateral triangle ABC be tangent to the circle at points B and C, then what fraction of the area of ABC lies outside of the circle? And I'll give you guys some time to think about how to do this. All right, so hopefully you guys have had enough time to read the problem. So we're going to quickly start by solving it now. All right. So we know that the first thing to note is that sides A, B, and AC of equilateral. The first thing to note is that sides A, B, and AC are tangent to the circle. And we also know that triangle ABC is equilateral. So that's also important. So we want to now find the fraction of the area of ABC that lies outside the circle. So if we remember, one auxiliary construction that we often like to make is the tangents of the circle. And as you can see, they already, in this figure, we've already drawn it in. But the interesting thing about this is that if we draw a line connecting the tangency point to the center of the circle, then they intersect at 90-degree angles. So as a result, that means that this side, as a result, since O is the center of the circle, and A, B, and AC are tangent to the circle, we know that angle ABO is right. And we also know that angle ACO is also right. So like this. Now, notice that since this is an equilateral triangle, we have that this angle is equal to 60 degrees, this angle is equal to 60 degrees, 60 degrees, that we can get this is 30, and this is 120. So now we want to find, since we're trying to find the fraction of the area of ABC that lies outside the circle, we can just set the side length of ABC to be 1 because it's a ratio and it doesn't matter. So we can get this as 1. And now what we want to do, so how we're going to be approaching this is we're going to find the overall area of the large quadrilateral, or ABOC, and then subtract the area of the sector, or BOC, where the area of the sector looks something like this part. So the first thing to do is find the angle area of quadrilateral ABOC. And we can do that by splitting this quadrilateral up into two right triangles, because we know that ABO is equal to 90 and ACO is equal to 90. Now, since we know that each of these is 1, since we know that AB and AC both have length 1, if we call this point the intersection of the diagonals, if we call it like X or something, then we know that BX is equal to 1/2 and XC is also equal to 1/2. And now, since this is a 30, 60, 90 triangle down below, we can get that OB is equal to 1 over root 3, or root 3 over 3. And we can also get that OC is equal to root 3 over 3. And the way we did this is by utilizing 30, 60, 90 triangles. So since the radius of the circle is root 3 over 3, and we know that angle ACO is right, then to get the area of triangle AOC, we know that this is equal to 1/2 times base times height. So this is equal to root 3 over 4. And since we know that the area of AOB is equal to the area of AOC, we can just multiply the area of AOC times 2 to get that the overall area is root 3 over 2. So we know that this part is equal to root 3 over 2. So give me a second. All right, so from here, all we have to do now is to find the area of the sector BOC, and we can do this because we know that angle BOC is equal to 120 degrees, which implies that the sector BOC is equal to 1/3 the area of the circle. 1/3 area of the circle. And since the circle has radius root 3 over 3, we can get that the circle has an area of root 3 over 3 squared times pi. So overall, the sector has an area of 1/9 pi. So plugging this in for BOC gets us that the area is 1/9 pi. So this is the area of the, so we know that this is the area of the equilateral triangle that does not lie inside the circle. However, we want to find the fraction of the area of ABC that lies outside the circle. So from here, we have to find the area of the equilateral triangle, which is just equal to, we can use the formula for an equilateral triangle to get the for an equilateral triangle to get that this is equal to 1 squared times root 3 over 4. So root 3 over 4. So our final answer is equal to root 3 over 2 minus 1 over 9 pi over root 3 over 4. And this is an unsimplified radical, but I'm sure that you guys can simplify it yourself, right? Because I'm too lazy to do that. All right, any questions, guys? Let's see. How did you get 30 and 60 degrees? So since we know that triangle ABC is equilateral, we know that all of its angles are 60 degrees. Then, since it says that sides AB and AC are tangent to the circle, we know that angle ABO and angle ACO are both 90 degrees. So from there, if we subtract the angles, we can get that 90 minus 60 is 30. So angle OBC is equal to 30. And we can angle chase from there. Did you make up the values because they weren't given? So the reason we were allowed to assume that side AB was 1 is because they wanted a fraction of an area. And since they wanted a ratio, then we actually have 1 degree of freedom. So it doesn't matter if we set the length of AB to be 1, because no matter the side length, the ratio will turn out to be the same anyways. So that's another helpful trick that you can use a lot. And yeah, any other questions? All right. If not, then we're going to move on to the next one, which is about an annoying rectangle thing. And unlike my kind of bad problem, this is something where this is a problem where auxiliary questions are actually pretty necessary. So yeah. So I'll give you guys some time to read the problem and think about how to approach it. Okay, so hopefully you guys have had enough time to read the problem. So now we're going to quickly start. So we're going to be starting by labeling all of the information that we know. So we know that side AB is equal to 5. And we know that side BC is equal to 4. The other thing we know is that EB is equal to 1. So we can set this equal to 1. And we know that AE is equal to 5 minus 1, which is 4. We also know that CG is equal to 1. So this is 1. So we can get that BC is 4 minus 1, which is equal to 3. It also gives us that DF is equal to 2. And we can get that FC is equal to 3. So from here, we want to find the ratio of PQ to EF. So getting the length of EF is actually pretty easy, because if we drop this altitude from E, then we get a right triangle. And since we know that the altitude length is 4, and we know that this length down here is 2, because 3 minus 1 is equal to 2. So using the Pythagorean theorem, we can get that EF is equal to 2 squared plus 4 squared square root, which is equal to 2 root 5. And I'm just going to quickly unruin my diagram real quick. So from there, we can get that EF is equal to 2 root 5. So now from here, we have to get the length of PQ. And the way we're going to be doing this is by making this small auxiliary construction to get some similar triangles by extending length AG to intersect with DC. And again, the reason for this is because if we call this length H, then we now get two pairs of similar triangles. We get that AEQ is similar to triangle HQF. And we also get that triangle HCG is similar to triangle ABG. So this is sort of like buy one, get two free. So from here, if we note this, So the first thing we know is that since HCG is similar to ABG, we can use the length ratios to get that BG to AB is equal to CG to CH. And plugging in our numbers, this gets us that 3 to 5 is equal to 1 to CH. So CH is equal to 5 over 3. So I know that this small length is equal to 5 over 3. All right. So from here, now we're going to use the other similarity, which is AEQ is similar to triangle HQF. So if we want to look at the ratio of the sides, we can again use the ratio of the lengths to get that AE to FH is equal to EQ to QF. And solving for this, we get that 4 to 14 over 3 is equal to EQ to EF. Sorry, EQ to QF, my bad. And now from here, the last thing we're going to use another similarity ratio, which is triangle AEP is similar to triangle FPC. So what this gives us is that AE to FC is equal to EP to PF. So this is, and plugging in the values that we know, we get that 4 over 3 is equal to EP to EF. So these are our two important ratios. And yeah. And the reason we were allowed to do this is because we drew in this extra side length, which sort of gave us two free similarities that we could exploit. All right. So now what we're going to be doing is using both of these to get PQ to EF. And I'm running out of room, so I'm just going to work up here. So if we call length FP as X, length PQ as Y, and length EQ as Z, then if we substitute in for these boxed equations, we get that 4 over 3 is equal to Y plus Z to X, and we get that 6 to 7 is equal to EQ to EF, which is Z to X plus Y. So from here, we can get that, from here solving, we get that 4x is equal to 3y plus 3z, and 6x plus 6y is equal to 7z. And if we solve for everything in terms of the other variables, we should be able to get that. So from the first equation, we can get that x is equal to 3y plus 3z over 4. And plugging this into the second equation should get us that. Okay, I'm going to quickly erase some of my previous work because we're running out of room. And plugging this in should give us that 6 times 3y plus 3z over 4 plus 6y is equal to 7z. And then if we do all the expansion and all that stuff, we get that 18y plus 18z plus 24y is equal to 28z. And then doing some simplification, we can get that 21y is equal to 5z. Now, if we plug this in, since we know that x is equal to 3y plus 3z over 4, if we substitute in for z, we can get that z is equal to 5 over 21y. So plugging this in gets us that, and yeah, this is a lot of algebraic bash, but it'll be worth it, don't worry. We can get that x is equal to 3y plus 5 over 7y over 4. Yeah. So from here, since we have both x and z in terms of y, and we note that we want to find PQ over EF, and we know that PQ over EF is actually equal to Y over X plus Y plus Z. So substituting in these values right here that we have for Z and X, we can get that this ratio that we want is equal to Y over 3Y plus 5 over 7Y over 4 plus Y plus 5 over 21Y. And from here, we can cancel out all of the Y's because every term in the numerator and denominator has a Y to get 1 over 3 plus 5 over 7 over 4 plus 1 plus 5 over 21. And this is our final answer. And this might not be a simplified fraction, but I'm just a bit too lazy to solve this simplified fraction. So you guys can do it for homework because I think that's a great way to do homework. So yeah. Anyone have any questions? Let me quickly check. How did you get EF? Should it be around 5? EF. Oh, EF wasn't actually, oh, whoops. This was actually kind of irrelevant to the problem, but the way I got EF was by dropping an altitude from E to DC. And when we get here, we know that EB is equal to 1. So we know that this distance, so that means we know that this distance right here is equal to 1. And since FC is equal to 3, we can get that this length right here is equal to 2. And since we know BC is 4, we know that E, the altitude from E, is also equal to 4. So we can use Pythagorean theorem to get EF, although that wasn't actually relevant to the problem. Can you erase all the marks after you're done so I can get a copy of this? I'll be posting all of the lecture problems to the Kid Teach Kid website later after class, so don't worry about that. Can I be lazy too? It depends. Although, you know, I think that since I'm probably like one of the most lazy people, so I should get some privileges, right? I don't know. When does the class end? In about 6 minutes, I think. Oh, and let me look at this poll. Wait, you guys actually like algebra? I'm surprised that so many of you guys like algebra because algebra is definitely my least favorite subject. So yeah, that's actually kind of, that's interesting. I did not know so many people liked algebra. Oh, and 13 people, apparently 13 people say that math sucks. So that's interesting. Okay. I'm not sure if we have enough time to go over the rest of the problems. So I'll probably just attach those to the homework or something. So do you guys have any questions or comments or something that you want me to review? What is 1 plus 1? I don't know that. I think I'm going to have to give that to someone else. I'm going to pass. Will I learn this in geometry? If you're talking about school level geometry, I remember that at least in my year, we learned a bit about similarity, although we didn't go too in depth. So yeah. All right. What grade am I in? Oh, I'm a rising sophomore. So yeah. Yeah. Does anyone want me to go back to any of the problems, or anyone have any? Is there any like confusion or anything? How many people are we? There's 140 people here right now. How many seconds are in 5 meters? A lot. Yeah. And if no one has any questions, then since we have 5 minutes until the next class, I guess we'll just you guys can quickly take a 5-minute break, or if you're not going to be attending the next class, then you can leave. But hopefully you will, because I think that's a good idea. So I'll open the chat for now, and then yeah, you guys can just chill out, play video games, do whatever you want for 5 minutes while we wait for Dan. And he's going to be teaching Java coding, so I think you guys should really pay attention for that because it's really interesting. Yeah. What is my favorite math topic? My favorite math topic is actually number theory, although I really like combinatorics too. I just don't really like geometry and algebra because I think that they're really annoying to deal with. What is my major? Oh, I have no idea. On a scale of 1 to 10, what is your favorite color of the alphabet? Probably like 2? I don't know. Oh, how do you get the length of GH? Wait, let me quickly see. So we were able to get the length of GH. If we didn't actually calculate for the length of GH, but if you wanted to, since we know that CH is equal to 5/3 and GC is equal to 1, we could use the Pythagorean theorem to get the length of GH, but we don't actually need that in the problem. Oh wait, did I disable? Okay. Oh shoot, whoops. Oh, okay, whoops. I meant to turn on the chat, but I accidentally disabled it. That was my bad. Okay. Let's see. Do we need to download Java for the next class? I'm not entirely sure what Dan has planned. I think it's recommended, although I'm not entirely sure if it's required. What grade do you learn this? Oh, most of this is from a AMC, a contest called AMC 10, and it's pretty much for, I guess there's not really a specific grade level that it's for, although it's pretty much, the AMC 10 is just a contest that's open to all students under the 10th grade. So I guess anyone under the 10th grade can learn about that. So yeah. Are you Flash Sonic? Possibly. And by the way, if you guys ever have any questions after class about the homework or just anything in general, then feel free to go to the Kid Teach Kid website and fill out the question submission form. And if you want to give us feedback on our classes, for example, if we're going too fast or too slow, then there's a student survey that you can fill out, and we'll try our best to adjust accordingly based on what you need. So yeah, since Dan is here now, I think you guys should all get really excited for his coding class, which is going to be really exciting. So yeah, thanks so much for listening. Bye guys.